All right, so we need to talk more about replication and consistency, of course, it's in the picture. Well, let me just point something out, which is kind of interesting. If we do no replication, we essentially have no consistency issues. Well, if you ignore the consistency issues within the same machine, but nevertheless, life would be much easier if you wouldn't replicate. So this, in fact, begs the question, why bother replicate? And fault tolerance is the big issue, together with performance enhancements. But you have to be careful, especially when you're selling replication as a performance-enhancing technique. You have to make sure that you're, in fact, achieving higher performance, which is not necessarily the case, right? So that's the first question to ask when you need to pick solutions for replications, right? Am I really getting better performance? I mean, there are other ways to, in fact, get some sort of protection against fault tolerance. Availability is one of the issues, but maybe not even your biggest problem. You can do backups and other things that can help with things besides availability, which you should be doing in the first place, right? It turns out that in general, it's hard to achieve performance, improved performance, right? We've seen this, for example, when you have to use some sort of total ordering of operations, right? It's so tedious in terms of how many messages needs to be exchanged and so on that you can easily see that the performance could, in fact, dramatically spiral down, right? If that happens, of course, the benefits of doing replication disappear very fast. So the fact that you're replicating doesn't mean necessarily you have a good solution. All right, so what I want to do in this class is start discussing some other issues related to replication and discuss some solutions for all those consistency concerns we had before, right? So we only talked about consistency models, but we didn't have any solutions. We only said you must take care of this without any indication of how you might do that, okay? So let's do some of these things. So one of the issues is replica server placement, and you can spend as little or as much time on this issue. I mean, that's true with almost any issues in this area, because there are no fixed, determined, provably good solutions in here, right? So the kind of situation you can have is the following, right? You have a non-uniform distribution of, let's say, clients. I mean, this could be geographical distribution or connectivity distribution or things of this sort. And the question is, how should you, in fact, allocate clients if you want to servers, at least for the normal execution, the normal functioning of the system, right? So most of the time, you would like the client to go to some sort of a maybe close-by server, and only if that server fails to use some sort of fault tolerance to move to another server, so on and so forth. Right? Now, I want to point out that these problems in various forms have been encountered in other areas. For example, cell phone technology, right? This is a really big problem for cell phone technology. You have to decide where you're going to put those big antennas, and what each of the cell phones has, in fact, through complex protocols, has to determine which is the tower it actually talks to. And if you don't have enough towers, this is when you actually get congestion, right? And of course, congestion in the cell phone network makes everybody very unhappy because calls get dropped and whatnot, okay? Depending on how the technology is put together, I mean, you might get a crappy phone call, or you might simply not get connectivity at all, right? But the same kind of issue can be put in different contexts, right? I keep on mentioning Akamai, right? Akamai is placing servers closer to the users, but for Akamai, it's very important to determine where to place servers, because none of this is free or particularly cheap, right? For Akamai to place a particular server in a particular, if you want, corner of the internet, I mean, they have to spend money, rent space, probably at the ISP, which is going to charge quite a lot because it's kind of prime real estate, right? So this replica server placement is very much tied with money, with commercial interests, right? And this is one of the reasons why it's somewhat studied in the research literature, but extremely well studied behind the scenes, and the solutions kept secret by the various companies that need to do this kind of things, right? So Verizon and AT&T are very concerned about, for example, cell tower placement, but now also about server placements. Akamai is selling the service in which they determine where to place the servers. Each particular company can, in fact, pose the same kind of a problem. And in fact, there is a problem that has been studied for close to 100 years, which has nothing to do with, I mean, not in a direct way with necessarily replica placement, but has to do with, for example, distribution center placement, right? So think, for example, about a large grocery store chain, right? Publix. Okay? So Publix actually has to take, when they expand and when they do various kind of things, they have to take some hard decisions with respect to where to place those big warehouses, right? So the trucks come to the warehouse, and then smaller trucks or different trucks go and serve each of the stores. And to a large extent, is the same kind of a problem. So if you have a densely populated area, right, which has many, many, many stores, then you better place more of these warehouses, and potentially of different sizes. You can add size of the server as well, capabilities of the server as well, right? Because otherwise, you're not going to keep all those stores filled. But if you have a sparsely populated area, right, you might actually place far fewer such warehouses. And one of those warehouses is going to cost you, I mean, probably in the $100 million range, right? So you don't really want to just willy-nilly place them in there. Now, the problem is not so bad for cell phone towers, and it's probably much cheaper when it comes to placement of the servers. And to some extent, you have a lot more flexibility in creating a new one, right? So the cost of creating such a resource has to be figured out in the entire story, which suggests the following kind of approach, right? These problems tend to be hard. I mean, it's known that optimal placement of such resources almost always is NP hard. You're all taking the algorithms class, right? I think it's on the list of the core courses, right? So trying to find the best solution is a little bit foolish in these kind of circumstances. A lot of them don't even have a good approximation algorithm, right? So good heuristics is kind of the best you can hope for that work in real life. And by the way, this is what Akamai is famous for. So Akamai was founded by theoreticians working on placement problems, on actually randomized algorithms for placement, which were essentially offering some kind of randomized guarantees. The algorithms, they prove nice things theoretically, but they realize they're actually very cute in practice as well. And this is when they started transitioning towards, hey, maybe we can actually figure out how to play the game, right? Now, for a company like Akamai, and you might be close to this situation potentially, at least some of you, for a company like Akamai, what's important is to be as lean as possible. Right? Other companies that do this kind of server placement can actually pop up. And what matters is who can save more money when it comes to this, because you can offer them the service at a better cost. Right? So being wasteful in placement of the servers and so on, right, becomes very problematic. I mean, it literally can lead to bankruptcy very fast for a company like Akamai. Okay? Now, similar problems are faced, for example, by the large if you want, cloud companies, which is about everybody now, right? For example, when Google decides where to put another big data center, right, they have to think about where do they need more capacity, if you want. So these problems are called, to some extent, capacity problems, right? So one approach, for example, is find congestions in the system and place more capacity right there. This is known not to lead to optimal solutions, but might be reasonably good, right? Right, so it's rumored, for example, now that Google is building some sort of a floating data center in San Francisco area, right? People have seen some barges that look suspicious. They ran out of land, I suspect, and there's too much stuff going on in that area, right? A lot of .com activity, right? But to a large extent, it's the same kind of problem. So I don't want to talk too much about this because, again, even theoretically, all these problems are actually very hard, and you can't really prove too much about them. A reasonable heuristic solution might actually go a long way. I mean, one of the problems is the following, and I want to point out the dangers of trying too hard on these kind of problems. So when you model this problem, you can model it theoretically as an optimization problem. This is the standard approach, right? An optimization problem requires some sort of a goodness measure or badness measure. And then what you're trying to do is say, where should I place the servers or whatnot in order to let's improve the, so you define a mathematical efficiency and say, where should I place the server so I improve the efficiency? Okay? Now that sounds very nice and produces very complicated papers and whatnot. But there is a really big problem with any such approaches. And the problem is, are you measuring the right thing? Okay? So what I mean by that is, OK, fine. So let's think about how do we define a cost of, let's say, or what's a benefit measure. So let's say I want to put a server, and I need to determine how much do I gain if I place a server there. I need some sort of a measure like this if I want to solve an optimization problem. Okay? So how am I going to actually measure how much better things are going to be if I place a server in a particular place? This turns out to be very problematic, right? Because it's not something that can be done with very simple equations. I mean, you could try to approximate it, and usually these approximations are quite rough, right? To a large extent, until you actually place the server there and you try to do whatever is it that you're doing and you measure how much money you spend, you can't really tell how much money you spend. Or let's say you want to improve things like latency and other things. Until you really place it there, there's so many factors. It's so complicated. The real setup is so complicated, you can't know for sure what's going on in there. Okay? By the way, there is a counterpart problem in databases where you want to pick the best plan to execute a query. But of course, that assumes that you can, in fact, tell how good a plan is if I just give you the plan, which turns out to be absolutely not true. Okay? So this points out to something that is usually not mentioned, especially in the more theoretical literature, which is trying too hard is not worth it. Even if you can actually solve perfectly the optimization problem, you might still solve the wrong problem because you can't measure, you can't tell for sure how costly it's going to be to do a certain activity in terms of anything you want. Right? You can define measures for which you can solve some of these problems, but they might not correspond to anything that's in real life. Right? It's really one of the big problems plaguing databases and plaguing any complex system. Right? So even ask yourself, hey, if I place another server, let's say in the department, I mean, could I tell for sure that some latency is reduced or some other things? Well, not really, because it's so complicated. Things go through so many wires, so much stuff. You can get some rough approximation, right? So that also suggests that if your approximation, and by the way, approximations within a constant factor are hard, right? So for example, in databases, nobody can guarantee that they can approximate the cost of a query within any constant factor. Right? Including, let's say, 10. You might not even be able to tell roughly the order of magnitude for the time running a query. It's that bad. So if that's the case, insisting on an actual optimal solution, whatever that means, for such problems, it's foolish, in my opinion. Okay? So basically, all of this discussion justifies, in a heavy way, heuristics. And this is, in the end, what this boils down to. It's a lot of common sense and some reasonable heuristics where you do it, unless you're Akamai, when they have some secret sauce in which they do some, at least they look cool, whatever is it that they are doing, right? Well, it turns out that their algorithms are, in fact, approximation algorithms that are kind of self-adaptive, that turn to kind of sense how things happen, measure as you go, and change, and whatever other stuff they are doing. I'm not going to go there. I mean, it's done by extremely sophisticated people from MIT, and a lot of it is secret sauce. They don't even bother to patent anything and so on. Right? All right, so this is the story with the replica server placement, but it's a real problem. Right? Now, there is a bigger problem that in general has to be solved, which is how do you grow capacity depending on things like the load? Right? So this is not even so much the static scenario you have here, in which you already know where people are and how they are, and you're decided to place another server. You might need to add capacity just because there are spikes in the usage. And this happens all the time. I mean, this is one of the big things that goes in favor of any cloud-based service. Right? They say, hey, no problem, you can grow capacity by essentially just clicking a couple of buttons, and then you fire up more websites on more, basically on more servers. And this is kind of the promise that Amazon EC2 is making, and is the promise that Microsoft Azure makes, and so on, right? They say, hey, you can spawn off as many servers as needed for a short period of time, right? So, I mean, that's one way to go about it. But again, all of these solutions have to be treated carefully. A big problem, of course, with cloud-based services, capacity growing, you're essentially renting capacity, is if you have an outage at the entire Amazon level, which happened, I think, about a month ago, then a quarter of the internet goes down because they're all using EC2, right? I mean, when it's bad, it's really bad. I mean, this is kind of the situation, right? Because an outage now in a big data center doesn't only affect that company, it affects everybody who was using their cloud service. All right. Now, replication, especially for performance reasons, is one of the main ways to improve performance. So it's extremely important to understand refinements in what can be done with replication. And this replication is everywhere. This is what I've been arguing throughout the class, and is mostly everywhere in the form of some sort of caching. Okay. So it's worth talking about some tiny decimal points in there to see what choices you have when you do various things. And I'm going to do something that the textbook writers don't, namely mention equivalent issues when it comes to computer architecture, things that happen inside the processor, for example. So it's kind of strange. Is why would a distributed system have any similarity to what happens inside the processor? Well, processors themselves are complex distributed systems nowadays, believe it or not, especially when it comes to multi-core. And a lot of these issues have to be solved inside the processor. You might have different solutions because you have a different trade-off, but it's the same issue in the first place. Okay, so I'll point out some of those things. So when it comes to replication, right, there are a number of things you can do. So the issue is what? The issue is when writes happen, when the content changes, how do you make the new content available? Right? And this is really the crucial issue, because if you have a stable scenario in which nothing changes and you're done replicating, whatever that means, then it's relatively easy. You can keep a personal copy. You keep it very close to yourself as long as you have enough storage for that, right? And then all you need to do is access the local copy. Not a big issue at all, okay? So that happens essentially all the time. So, I mean, even basic stuff like, for example, when you install the operating system on your machine and you're not keep on getting the files from some internet website, that in itself is some form of caching, in fact. Okay. You could actually, with a very small kernel and a distributed file system, in principle, get all of those things from the cloud, but it looks so foolish, right? Now, the technology is in the favor of caching when it comes to size, when it comes to capacity, because hard drives are cheaper and cheaper, right? It's almost unheard of not to have at least half a terabyte hard drive in essentially any machine, unless it's an iPad or an iPhone, right? Laptops without at least half a terabyte. Unless you have an SSD and maybe you get a 128. But in any case, you have a large amount of storage by at least 10 years old standards when it comes to local machines, which essentially means that one of the big obstacles to replication is removed, namely storage. It's cheap, right? So when it comes to things like replication, the more problems you have to solve, the harder it gets and the bigger the mess up. Right? Potential problems with replication is decide what to replicate, right? So the first one is what, right? And there is a how question, right, and which we are going to discuss. But at least the what goes away if you have large storage for the most part, because even if you're not sure that it's going to help, you can still replicate it. If you got your hands on it, you can still replicate it, and that's it, right? So what I mean by that is, in most devices, unless maybe you have very, very small devices, if you bothered to bring it, you might as well keep it, and you can keep it for a while. And this is literally what caching in the web browsers does, what a lot of other caching techniques would in fact do, right? Now, the how, it's still very important, right? Especially if you are concerned about bandwidth. And to some extent, you have to be. So bandwidth is going up. So you don't need to be paranoid about bandwidth anymore. But nevertheless, there are some concerns. Now, you don't need to be paranoid with respect to the bandwidth for the clients, but you still have to be paranoid with respect to the bandwidth for the servers, by the way, depending on how many clients actually access the same server, right? So it's very easy to say, yeah, we have now a lot of bandwidth, so on and so forth. Well, yes, but not if, for example, you're serving 1 million people from just one server, which is, in principle, possible, and some people pull that out, right? So if that's the case, you really want to have as little as possible messages going around there, okay? So when it comes to this kind of replication and these placements, right? In the middle, we have this, if you want, the permanent replicas, is where the content really lives. In the outer ring, we have the clients. So somehow the clients have to get their hands on the data that resides in the permanent replicas, right? So the information has to be propagated correctly. But such propagation can be initiated in two fundamentally different ways, right? One of them is client-initiated replicas. and the other one is server-initiated replicas. Okay? So this is pull. When the clients pull the content when they need it, this is push. The servers will push whatever it is that they push to the clients. Okay? And it turns out that in most sophisticated applications, you in fact have to use a mix between a pull and a push. I'm going to explain a little bit why that's the case. Because for certain kind of things, it's better to pull, and for certain other kinds of things, it's better to push. Okay? Now, you can do a pure push-based system and a pure pull-based system, but you're essentially giving up on some big characteristics you might actually care about. Okay? So let's just think about how this might actually work. So the one you're most familiar with is, in fact, the client-initiated replicas, because it's essentially what's happening by default in web access, right? So when you take your browser on any device you have and you point it to some kind of a URL, what is it that you're doing? You're going to the server and say, give me the content of this resource. I mean, resource usually means some sort of a URL, which you can't even say now that's a file or something else. I mean, it could be something completely cooked up on the fly, right? And as a client, you can decide to do some sort of replication. I mean, you have to, I want you to understand that there's no ifs and buts about it. You have to do some sort of replication, because you can't get it every frame, right? So, I mean, if you want to be paranoid, literally you can say, you know what, I want to have the freshest content. So what I'll do is I will keep the content 30 milliseconds, exactly how much it takes me to display a frame on the computer, no more. I mean, why 30 milliseconds again? Below 30 milliseconds, human eye cannot, right? If humans are your clients, it's 30 milliseconds. By the way, if you're doing extremely fast trading using these fast bots, you might decide to cache less than a millisecond. Okay? So it's all kind of depending on the application, right? But of course, that would be crazy. I mean, imagine your device that you use to access the internet trying to get something every 30 milliseconds when the delays can easily be in half a second to a second to a lot of the servers, right? I mean, nothing would actually work. So you can think about caching at many, many, many different levels, including things like the sophisticated, complicated UI that the web browser displays on the screen. I mean, it's not only the basic replication that you might think happens, right? Namely that you got the HTML page or whatever JavaScript code or whatever is it that you're doing. But it's caching all the way between the server and consuming the content, right? So there is massive amount of caching that happens, for example, in the web browser itself. I mean, the web browser has to be as lazy as possible about what gets updated and what doesn't get updated, and try to keep as much as possible static, not changing, because changing everything all the time, right, it's a big performance hog. So web browsers got extremely sophisticated at determining what not to change. Okay? It's very easy to change everything. You just say, fire up the whole processing from scratch. But if you do so, you suffer big performance problems. So finding large areas of the screen that do not change for sure and not firing up any kind of updates in there, it's a big performance improvement measure. So that's some form of caching, but you're caching now pixels on the screen, if you want, not actual content in the backend, right? So it doesn't matter how you call this technique. Being lazy about how these changes get propagated, right? It's one of the best ways to improve performance. Okay? Good. So this is really what client-initiated replicas are. But then you have a big problem. And you might not even realize, but these are big questions that people that wrote even web browsers had to decide. It's clear that you do want to cache things that tend not to change, because that will significantly improve performance, right? So for example, these web applications, right, they have large amounts of JavaScript code. I mean, it makes a lot of sense to say I'm going to cache that large amount of JavaScript code, because bringing all that all the time, I mean, it consumes resources. On the other hand, you might work on stale copies. So a big question when it comes to replication is when to replicate, right? So we have a what, how, and when. In particular, the big question is when to invalidate whatever copy you have. Right? Now, this problem is in fact very old, because one of the main techniques inside computer architecture systems is caching, right? So a big question there is, how do you deal with information that's stale? Right? So there are two primary techniques. One of them is before you use a copy, for example. I mean, there are multiple techniques, but one of them is before you use the copy, you could try to check, and maybe the check is faster than using the resource. You can try to check to see if the resource is stale or not. And that's still a pull kind of technique in which the client is trying to figure out, do I have a stale copy or a good copy? Okay? So some sort of a check. Check for freshness. The other one is to say, you know what? I'm going to assume that my copy is fresh, but I'm going to have whoever could change the content send me some notification when the copy is invalid. I think I actually have a picture for this. Let me see. Right, so something like this. I'm going to go back to the other one, right? So this is notifications. And then, of course, you have the full technique that corresponds to notification is push full changes. Okay. Now, when you're talking about check freshness, you can have various algorithms to check freshness. And in fact, for example, web browsers have at least a workable solution for that, right? So their solution is basically the following. They're trying to be quite lazy about it and try to guess when they should check for freshness, because the checking for freshness is itself expensive in terms of latency, right? The latency is what kills any of these things. If you have enough bandwidth, there might be almost no difference between checking for freshness and bringing a new copy, okay? So you're trying to be as lazy as possible for checking for freshness, but in the web browsers, for example, if you reload the page several times, you kick in a mechanism that will bring new copies of everything, because I mean, you need some sort of, you know what, don't give me the cached version, because for some reason I'm sure that there is a better version, right? And that will force some sort of, OK, invalidate the caches and go bring new versions of these programs. Okay. Well, I know this because when you do web development, right, this is your best friend. Otherwise, you keep changing the backend code, and the front end doesn't change anything because it decides to cache for 6 days, right? In 6 days, my application is going to be very different. So, OK? Now, these two solutions are very different than this check for freshness. So check for freshness is basically you lazily, at whatever times you check for freshness or look for indicators that something changed, and when it changed, you can decide to bring only what you need. Okay? So this is completely driven by what's in fact accessed. Okay? Now, this one, notifications and push changes, are driven by the server, and then you have hard problems to solve on the server now. Okay, so the hard problem is, one of the hard problems is, who should you push the change to, either the notification or the change? In particular, who is interested in this resource? So that's not clear at all, by the way. So, for example, web browsers were not designed to give any indication of who's interested in such a resource, unless you do special programming, right? So the fact that I access some web page doesn't mean I need to be notified every time that web page changes, and that would be madness if that's the solution used everywhere by most of the websites, right? It's, hey, CNN updated their main web page. You should definitely do something about it. I mean, it doesn't work that way. But for example, imagine, though, that I am watching, for example, stocks, right, the prices on the stock market, right? Then, well, I'm kind of on the web page of those guys, whatever that means. I might actually be interested in updates because I'm interested in those events. Or imagine a chat application, for example, right? In a chat application, I really want to know when somebody else chats without me keep on saying, OK, so I waited already 3 seconds. Is there something more? And that would be essentially invalidate my state, which is I only know about my chats, and go see if there is any other chat. So for certain applications like chat, notifications or, in fact, completely pushing changes make a lot of sense. For other applications, only check freshness might make any kind of sense, right? So this is the kind of things that you would have to ask yourself almost always when you design an application, which one do you do? Now, when it comes to notifications and push changes, you, in fact, require a special facility in the server, right, which we did not talk extensively about, but you require so-called stateful servers. Okay? So stateful is the opposite of stateless. So it's easier to explain what stateless means. Right? There is some kind of gradation in between, but stateless is very easy. Right, so stateless server it's a server that keeps no information about the clients. It gets a request, satisfies the request, sends the result, and forgot about everything that happened. Now, there is no such thing as purely stateless server because they all log something and whatever, but they're really not going to analyze their own log. So even if they log, it's an external activity that goes on to see what was in the log, right? Most of the web servers are designed to be stateless servers, right? And by the way, that's a really big problem with some of the modern applications because the request comes. Every request is completely independent of all the other requests. Every request is treated as essentially a pure function. You got some input, you go, you cook up whatever is it that you're doing, and you send back the result. Yes? I'm sorry? What? Cookie? Well, OK, we'll talk about the cookies in a second. OK, so that's blending things a little bit. But cookies only help with one issue, but it's not going to add too much state. OK, 1 second. Right? So, for example, Apache and other web servers were designed to be stateless servers. Now, of course, you can't really do anything with purely stateless servers. And normally, the usual architecture is, I mean, this is the classic architecture for a web server. And it's extremely relevant for these kind of issues. Right? So you have the web browser who talks through the internet, whatever that means, with the server. And inside the server, this is the architecture you're going to have. You're going to have Apache, let's say. So let's say the web server, right, that actually gets a request. If multiple requests come, you essentially fire up different processes or different threads depending on the implementation of the web server. But they don't talk to each other. This is the classic web server architecture. The web server is going to fire up some sort of a language behind the back. I mean, if the job is easy, namely just serve a file, it will grab the file from the file system and serve it back. So it could go, let's say, to the file system and then send it right back. Well, it's really through the web server that happens. Or you could go to, for example, if you want to serve dynamic content, you might go to something like PHP. All right? So PHP is going to carry out some computation that's going to do something, which I'll mention in a second. The important thing is PHP itself, it's going to be stateless in the sense that you create a PHP session, it does something, and you destroy the PHP session. So there is no state carried through the session itself. Even if you have tricks, for example, to keep the PHP alive more, right, you're still wiping out the state. Now, this is not going to be very good if you need to, for example, keep track of transactions, I mean, moving money around, buying items, and so on. So somebody must keep some sort of state. But that, in the traditional architecture, is done through some sort of a database backend. So you have a database backend. And in fact, what's going to happen is you have connection to the web server to PHP. It's still stateless. PHP is going to do operations against the database, and it's the only one that actually maintains state. And it's the only one where states fight with each other and where you have concurrency problems. And then the whole thing comes back. So this doesn't keep any big information. This doesn't keep any big information. This keeps all the information. So this is stateful, but it's consolidated into the database. So any fighting that goes on and any consistency issues are only resolved at the database level. Now, I did mention before that database technology is many years ahead in terms of consistency than anything else. And this is really why it's the preferred way to, if you want, solve consistency problems. So you have no consistency issues here and here for the most part because they are stateless, and you push all the consistency issues in the database, which is reasonably mature technology. Okay? Now, why do I say almost? Because of this cookie stuff. Okay? So, I mean, what are these cookies? And what are they used for? By the way, they're kind of going away. I mean, there are better solutions than cookies now. Right? I believe you can do much better than cookies. Well, so this has to do with the fact that it's extremely annoying to repeat the same operation many times for humans. So what I mean by that is, imagine that you need to restrict access. So a big problem with any kind of security, and we are going to talk extensively about this, a big issue with any kind of security is the moment it becomes annoying, people don't use it. Okay? So how do you make security secure and not annoying at the same time? All right? So what I mean by that is, imagine that, for example, you're on eBay. Yes? But every time you click on another page, I'm going to ask again for the password, validate for that one request that you're who you are, and go and serve the page. I mean, first of all, it's not clear at all that I have a single request on a web page, and I might have many, many different requests. But let's say not all of them need to be secure. Okay, only one of the requests. But even typing your password every time, you're going to go insane. Right? Not good. So what cookies help with is to create some temporary validation once you typed in one of these passwords to say for the next whatever amount of time or until such right is revoked, you don't need to type a password. Okay? Now, that's a technique used, for example, by Mac OS X. Once you log in as an admin for a couple of minutes, you're an admin. Now, that's done for the sudo program, right? That's true also on Linux. Once you successfully log in into sudo, depending on the policy set in the system for a couple of minutes, you still are sudo. And if you keep on doing things, you're fine. But the moment you have a gap of whatever it's set in the system, then the privilege goes away. Okay? Now, usually cookies live a lot longer. I mean, some websites use cookies that stay alive a month or whatnot. Now, that's what cookies were designed for. What they are used for, it's a much more abusive thing. Okay? Keep track of people and whatnot. Okay? Right. So cookies are, to a large extent, poor man's state something, right? So the server needed to keep a little bit of state, and they invented these cookies to allow the state to be kept track of. So what's happening with the cookie is, by the way, is the server itself is still reasonably stateless. The cookie is stored on the client side, and the cookie is sent with every single request automatically. So instead of having the user type all the time something, you simply have the system present the cookie, which is now cryptographically secure, hopefully, right? So the cookie will fly with any request. The server will check that the cookie is valid. That will be, if you want, the certificate that, yes, you can access the website under certain credentials. But it's not something that the user does, which is important. So a lot of issues related to security have to be solved through these automated mechanisms, right? Because that will make it a lot more bearable for the user. Increases a little bit the bandwidth and maybe decreases mildly performance, not even that much, okay? And the web server itself, it basically is going to store the valid cookie somewhere and compare any cookie with the valid cookie to see if it's valid. So it has a little bit of state, okay? Now, it turns out that this is not the only way you could do things. You can, in fact, have, and sometimes it is highly desirable to do so, you can, in fact, have stateful servers, okay? So a stateful server, it's a server that will stay alive all the time. By the way, this server, it's only kind of alive. It listens on the port, but it doesn't have the state up, right? And it has to fire up big machinery, or maybe it's doing some kind of clever tricks not to fire up so much. But for the most part, it's wiping out its memory on every request. You could, in fact, have servers that don't wipe out anything, and in fact, try to aggressively keep things in memory to speed things up. So one particular technique for the server would be, don't be so stateless. Cache yourself a lot of the things that otherwise would be used in memory, right? Because then you don't have to go to your disk or something else, and that will speed things up, at least on the server side, right? And in fact, that's what is needed for something like chatting, right? So when it comes to chatting, you really want to do this push changes. But if you do push changes, then the server cannot be stateless, really, right? Now, you could still do something like this in which all the state is pushed in the database, right? But I mean, the big question there is, how do you push state? So the pull, it's easy. The client makes the request, opens a TCP AP connection, right? It goes through, this guy was listening, fire up one of this, fire up one of this, depending on which part of the website you access, fire up the connection to the database. The database is always up, right? That guy stays up, right? And then the reply goes back. But if it comes to pushing, how do you push? So you must have built-in mechanisms to produce such pushing, okay? Now, before I go into details, let me point an interesting use of notifications, which is highly non-obvious. So the difference between notification and push changes is you're not really saying, here is everything that changed. In a notification, you just say, the copy is no longer valid. You're not saying how it changed. You just say, your copy is not valid, which essentially means notifications have to be paired up with a mechanism that pulls another copy. So it's a push notification pull request when you need it, right? So such a mechanism would essentially indicate that, oh yeah, that JavaScript file that you were accessing before is no longer fresh. You need to bring another one before you do anything else, okay? So notifications are in fact used in the memory architecture of most modern processors. Okay? The reason is the following. So by the way, it has a completely different name. And it's called cache invalidation. And it's part of the cache coherency protocol, right? So as part of the architecture, it has something called cache coherency. And one way to do cache coherency is to do cache invalidation. Right? So literally, cache invalidation is a mechanism in which the processor will say, this thing that I'm caching is definitely not good anymore. I need to go bring another copy when somebody accesses it. Okay? So it turns out, I mean, the actual way things happen, it's a little bit different. But in fact, processors are snooping on the communication channel, which is actually very complicated. So the snooping, it's a complicated thing, right? And in fact, are listening for any activity that overlaps with what they actually cache. And if they see any activity, they invalidate their own cache. So they know they would need to go and grab the real copy when they need one. Now, this is a better mechanism that, in fact, paying attention to what's going on and pushing their own changes, right? Because that's a lot more resource consuming, right? So it's, again, this difference between notification and push changes. So instead of pushing the full changes, forget about that. Essentially, what you're doing is you're betting that you don't necessarily need that resource right away. You just want to ensure a certain kind of correctness. For processors that share the same memory, for cores that share the same memory, this is extremely important, right? Because if you wouldn't enforce this kind of cache invalidation and to make it correct, you're going to have arbitrarily bad behavior going on in there. I mean, your work on somebody changes something in memory, but in fact, some other processor was caching it and it doesn't even notice, right? So that's a disaster. But I want you to understand that these cache coherency and cache invalidation protocols have the same problems at a high level as you have with these things. I mean, a lot of activity you just to keep up to date. And this is why, for example, you do see a shift now, at least for certain products, away from cache coherency protocols, right? So, for example, the PlayStation 3, the cell processor in PlayStation 3, the actual cores, the computational cores, have no cache whatsoever. The reason is this is very expensive, so they have to do explicit transfers. Transfer this big block of memory, right? So it's more like, not even check for freshness, but it's kind of planned. You do this, I transfer this portion, I do something, and I push it, okay? All right, now coming back to our chat server, right? Of course, you want to do the full push changes. Well, it kind of depends, right? So you want to push changes if they are relatively small, but maybe some notification or only a skeleton for the change if they are really big. Right? Being lazy about these things pays off big time, right? So if you all the time you have to transport big things just in case the user wants to use them, that's not a particularly good policy. So always when you design applications like this, you have to think about how big the propagation, the information is. If it's very big, I might be better off by knowing that it changed, maybe not quite notification. The important stuff gets pushed, right? So an intermediate solution between a push change and notification. So the things that are more visible get pushed, but the big content is not. So if you're trying to access it, you already, in fact, invalidated the cache for that one, and you do some sort of a separate request to get that content. And that seems to be a better solution. Okay? So in order to support this kind of things, right, notification-based kind of activities, for example, there is a brand, well, not quite brand new, it's about 5 years old, maybe about 7 years old now, right? There is a new mechanism supported by the web browsers to allow you to, in fact, have a continuous communication with the backend and get this kind of notifications, okay? And this is called web services. Well, is it? No, web sockets. So the normal operation in a web browser is a TCP IP connection that goes from the client, make the request, and then finishes, with some gizmos to make it faster, potentially, for example, bundling and so on. But they are still treated completely independently. Okay? WebSockets are completely different. WebSockets are a point-to-point connection between the client and the server in which the communication goes both ways. Okay? So in a strange way, the client itself is now a mini server. You literally have to listen on your own WebSocket to see what goes on. Right? So you can, in fact, say, you know what, listen on the WebSocket, and when something comes up, I can look at what comes up and then do whatever is it that I'm doing. Now, of course, this WebSocket is not possible without JavaScript. So you must have an active program here and not just some sort of a simple client that gets an HTML page and renders it. You must have some program running, right, in order to do something like WebSockets. But if you do, then a lot of things become much more straightforward, for example, like a chat application. Without a chat application, right, in the good old days to implement a chat application, you had to do something very nasty. You had to artificially invalidate the HTML page by setting a very short time for the cache, just a couple of seconds, to make another request, and then the server somehow to figure out how to render the new HTML page to reflect the new changes, right? That produces extremely nasty behavior. I mean, first of all, when the page gets invalidated, most web servers will make the whole page flicker. Right? This is how you know if they do magic with some of this stuff and maybe JavaScript to render parts of the page, or they load the whole page. If your entire page flickers and you see it get blank, I mean, almost blank, and again, you know they are loading a full page. If you click around and nothing flickers except some content changes here and there, you know that they are doing JavaScript magic and quite possibly using this kind of WebSockets. So I mean, by the way, the technology from the point of view of the user is quite simple in the WebSockets. I mean, very simple API will allow you to basically register a listener. It's exactly like a TCP/IP connection. You register a listener. You have your own way to speak on the wire, but you register a listener and I say, hey, when something comes, get the content and then do whatever you want with the content. I mean, interpret it as a string, or more interestingly, as some kind of a JSON object that can become data, right? You can do a lot of magic with these kind of things, right? For example, one of them would be to do a notification mechanism, right, when things changed, right? So imagine, for example, you're watching stocks. Such a WebSocket will allow, so you're watching stocks, and you're only interested in, I don't know, 5 tickers. You could, in fact, tell the server, through whatever mechanism you want, either the WebSocket, which is bidirectional, or through one of those calls. You can tell the server, hey, I'm interested in this kind of things. And then the server, maybe hopefully it remembers what you're interested in and somehow only pushes you changes that you're interested in. Okay. Now, we need to discuss about that separately, and I want to come back to that. That's called publish-subscribe system. But you see, everything is tied up to this notion of if you have a stale copy, I somehow have to make it available to you, either pull or push. So this is going to be a lot of pushing with publish-subscribe, right? So just to give you a short preview, a more elaborate publish-subscribe system is, for example, some sort of news feeds in which you say, I'm interested in this kind of things, and then you have a big server, and the server over thousands of millions of clients is determining who needs what at what time, and through the notification mechanism pushes things, right? Okay. All right. Now, of course, the trick there is only to let people know about things they care about, not about everything. Right? So it's the difference between a broadcast or some sort of multicast or point-to-point connection. All right? But all comes back to this, essentially to this replication. Right? So obviously, a publish-subscribe system is going to be implemented in a very different way than normal, for example, web content delivery. Okay? So any questions about this? Right? So this is the basic technique. You either check for freshness and you have whatever algorithm to detect for that, notifications which are small, or push full changes. Now, you can be a little bit clever in between, especially for resources that tend to be big but with small changes. Namely, you could send a set of operations that can be applied at the other end in order to bring the copy to a consistent copy, rather than the full copy, right? For example, these kind of things are very good for, let's say, file editing. When you're editing a file, especially this new trend, right, with the collaborating editing, you're usually making relatively small changes at any given moment of time. So it's going to be foolish to say, you know what, we work on this document and it's a megabyte in size. The moment somebody presses a key and puts a space in the document, I'm going to send you the new version of the document, right? So an interesting kind of question to ask there is, could I propagate only the small changes? And then there is a question of how you propagate those changes to keep multiple consistent copies when you have multiple, if you want people or processes that actually change the thing, right? So then you can be somewhere in the middle in which you're not invalidating the cache. You're not saying, hey, there is a change, go grab a new copy. You're simply sending a compact description of what changed, right? So some sort of a differential between the server copy and your own copy. That could potentially save a tremendous amount of bandwidth. And this is one of the core problems, for example, that the Box and Dropbox people need to solve, right? Because most of the files are going to have relatively small changes, continuous changes. If you only send the delta and you resolve correctly the changes on the other end, you're going to save tremendously on the bandwidth, which means more profit to you because you're literally going to be driven by the bandwidth itself. I mean, that's the big problem for Dropbox, right? It's bandwidth. Okay. Now, Dropbox is an interesting example, which it's probably worth discussing how exactly it fits into the story, right? The discussion should be probably more elaborate when we talk about distributed file systems, but essentially, because you can have a lot of storage locally, right? I mean, I just argued that hard drives are cheap. Most of the files you're accessing, especially if you don't pay a lot of money to Dropbox to have a very large storage, which is the case with most people, right? Then storing your own local copy is not a big issue, as long as these copies, your local copy and the server copy, are kept in sync, right? So the annoying thing would be if I change the files from multiple machines and the changes don't get propagated. I'm not really particularly concerned about the fact that I don't have space for my own copy, right? I mean, most people keep less than something like 10 gigabytes. 10 gigabytes now, I mean, even phones can do 10 gigabytes, right? Kind of, but, right? In those kind of circumstances, the big issue is how can you update those files, right? You could use notification to invalidate them, and then you force somebody to go and bring a new copy. You can use notification in other ways. For example, in Dropbox, I notice it uses it. You can have this other applications that when there is a notification, instead of just doing something in the file system or to complement what you're doing in the file system, you pop up something on user screen and say, hey, somebody is changing that file. There is a new copy for this file. Do you want me to bring it? And you still ask for some user action, which essentially means you're not wasting bandwidth unless the user really cares about that resource. So that's one way for, I mean, it's something that I think, at least initially, neglected as a solution. User engagement. If people have to click, right, then you can save a lot of bandwidth. Because people are going to go and click and click and click only for the first few days, and then they get tired, and they go and click only when they need it, right? You send a short notification. The user knows that it changed. It has to click on it to bring a new version. Saves bandwidth, as opposed to automatically keep on pushing these changes, right? Now, in fact, a company like Dropbox would have to do full push changes for binary files. It's usually very, very hard to send delta changes, right? Especially when you have compressed files, it's a complete disaster, right? Unless you know precisely the compression format and you're trying to do something probably too clever for your own good, okay? Literally, a small change in the file could produce quite large changes overall. Or if you're talking about encrypted files, it's a complete disaster, okay? Because possibly the entire file changes at the smallest change in the content if it's really encrypted. Even if you use block encryption, you're still dealing with blocks, right? So there is always some sort of a gradation between these things, and finding the right trade-off between these things is one tricky thing, right, for the specific application. Finding how and when to invalidate the caches is another tricky thing. And almost always these things have to be fine-tuned for the specific application. So don't look for canned solutions that work in every circumstance, right? It's a big struggle to find exactly when to check for freshness in particular applications and when and how to propagate these changes, okay? Right? So big issue and some sort of a continuum of solutions in there. Already had that discussion. Now, we don't only, so this is another issue, right? We are talking about the more general replication for the purpose of fault tolerance. When it comes to that, we really want to think a lot more about the server replication, right? So it's not only this story when you have the client replication, right? But when you have multiple servers and you're trying to pass the load on multiple servers for performance reasons, or you're simply trying to have enough redundancy in the system in case things get lost, right? Then the question is, how should you propagate information from one server to another? Okay. Now, let me tell you an interesting kind of story about client replication that can service even as a fault tolerance replication. It's kind of an interesting situation. And that could happen to you, but it happened to the people at the Pixar. Right? So it turns out that somebody deleted, by mistake, but nevertheless deleted, the entire creative content for Toy Story 2. Right? And somebody did some maintenance on the server and simply destroyed everything they've been doing for 2 years or something like that. That essentially means, by the way, instant bankruptcy for a company, a young company like Pixar at the time, because that means we don't deliver the movie or we deliver it late. You can't do it twice, okay? We deliver it late and that's it. We might as well call it quits. They were saved by the fact that one of the employees took a copy of the entire content home so that he can work on it. So this can, right? And then basically they started crying and somebody realized that they did something that probably was against the company policy and took all the files home. That happens, for example, when you're using, let's say, Subversion or Git or one of these tools in which you're essentially keeping your own copy in which you can make changes, but you're synchronizing with a server. If the server runs amok, which it might, right, at least you have your own copy, which in fact contains the full history. And you can actually recover most of what you had there, maybe minus a day or two from the backend content. So don't neglect this possibility that you could recover information in order to provide fault tolerance from cached copies. The cached copies themselves are, in fact, copies. If you have a way to resolve how good they are and what they are, and you can patch a solution together, it's not necessarily a bad solution. I mean, the alternative might be to just not do anything, which would be a complete disaster. Right? It's kind of an interesting, not meant, but possible use of caching. Okay? Right. Now, when it comes to servers, the question is how do changes propagate? Now, the client is the client, and from the client's point of view, you can think more in terms of some sort of caching, right? But with the server, and especially when database servers are involved, right, things can become a lot trickier. Why? Because of the consistency that needs to be enforced. Now, there is some sort of an implicit consistency when it comes to the user, but somehow everybody bends the rules a little bit more, right? So it's somewhat more acceptable to bend the rules when it comes to the client, but that's almost never acceptable when it comes to the servers. Now, when it comes to this kind of replication, right, there are multiple things you can actually do, and they have different properties, right? I mean, this is just a schematic that basically provides some sort of an adaptive way to server load problem, right? So I mentioned the initial problem, right? Where do you place servers? And how do you pair them with clients? Well, one technique, and this turns out to work reasonably well, is, you know what? Forget about trying to be smart from the beginning how I place servers. What I'm going to do is monitor how the server is used. When I detect that the server is struggling, I'm simply going to initiate some process of replication and partitioning the set of clients that go to the two different copies in order to alleviate the load, right? Now, of course, in order for that to work, you need some mechanism that ensures that that actually kicks in, right? Basically, and this is what I tell other people in other circumstances, is nothing exists unless somebody builds it, right? So the fact that it would be nice to have that doesn't mean it exists and it's there, right? So I mean, some people build mechanisms like this, or sometimes you have to initiate them by hand. So for example, if you really want to rent more capacity, literally some human has to determine that, hey, that's not enough, and let's add some capacity. Or maybe build some kind of a semi-automated mechanism. So this is one such mechanism, automated mechanism, right? So what you could do is measure the load. That can mean anything, but maybe something as simple as simply count how many clients, how many simultaneous clients you have at the same time. So keep some statistics. Or, I mean, this is something that, in my opinion, should happen all the time, and it happens almost never. Every large system should monitor itself and monitor its environment in order to detect, am I running in trouble? For example, as a server, what could you monitor to know you're running in trouble? Well, you can look for all the signs that indicate you're running in trouble. For example, you can look for CPU utilization, and if you're all the time at 100%, you're in trouble. You can, I don't know, look for delays to the hard drive, and if they are very large, you're in trouble, right? You can look for network congestion, right? and then you're in trouble. And all these things can determine you to say, hey, I'm going to initiate some sort of a replication mechanism, right? And then how the replication happens is a completely different thing. So monitor and replicate if you need to. This seems to be a technique that works reasonably well. Now, again, it does not produce optimal solutions. But then I argued at the beginning of the class that then you might not have such a thing as optimal solution because you can't measure things perfectly, right? So there is a saying in the database community is you don't want optimal solution, you want good enough solutions, or you want non-disastrous solutions, right? So the nightmare scenario is when such protocols, such algorithms that are doing things go into really weird territory and start doing very foolish things. Right? So for example, replicating a server for every client, that would be a disaster. I mean. By the way, a single line of code mistake could easily lead to, create a server for every client. I'm sure it happened to some people. Right? This is where defects and bugs come into play. Right? All right. We talked about this. We had a long discussion about this. So one particular, OK, so if we replicate the data, but the data is read-write, if it's read-only, it's easy. Right? We've replicated it. Maybe we have a clever algorithm, maybe a dumb algorithm to decide where we place another replica. But then that's kind of the only issue. Right? But when we have changes, these changes somehow need to be propagated, or the clients have to be made aware of such changes. Right? So if the client will check, but again, the client connects to one of the servers. If this server doesn't know about the change, and the change was initiated in another server, then you're in trouble. So the servers themselves have to somehow keep the information in sync. Okay? There are multiple techniques to do this. And this is exactly the notion of consistency that we talked about before. Right? Multiple techniques to do such things. And it really depends on what blend you have between reads and writes. Right? So one such technique is called remote write protocols, in which you have a primary copy. So the idea is basically the following. You're going to replicate the information essentially on all the servers, mostly for the purpose of reading. But when it comes to writing, only one server it's allowed to write, and initiate maybe a more global write, propagation of writes. But instead of saying you can write anywhere, for every item, you are allowed to write it only if you want in the home base of the item. Now, it turns out that that simplifies protocols between the servers. Right? So in particular, enforcing a notion of consistency is now much easier. Why? Remember, before, a lot of the problems came from the fact that I write in this server, and there is a concurrent write in another server, and then you can't put them together. But if every item has a home base, then only one server can actually write it. Right? So all the write requests will go to that server, and that server has to initiate any further propagation of the information to other servers. Your only issue is going to be mildly stale information in the other servers. But you're really not going to have most of the conflicts you would otherwise have if you have a primary base for where the writes happen. Okay? Now, that immediately means that writing is going to be a lot more expensive than reading. And a big question for the client is the following. So the client initiates the writes. I mean, the client does something that initiates the write. When can you let the client continue? Right? Now, this is a big issue in general, right, when it comes to asking any other entity to do some activity for you. And it's the discussion we had throughout the class, synchronous versus asynchronous operations. Right? Asynchronous means I ask you to do something, and I go on immediately and do something else. And you're eventually going to do it and whatever. Synchronous means I'll wait until I'm sure that you've done what I asked you to do, partially or completely. Right? Now, writing synchronous programs, it's much easier when it comes to reasoning about what goes on in the system. For example, when I ask the system to read something from the disk, right? It's much easier to say read, and when I get back the control that I would get, for example, in a synchronous system, I know that what I asked the operating system or the server or whatever to read, it's there because I waited for it. But now imagine that you would write code in which you say read, but the read will come in the future, but you immediately get control back. What would you do with it? You already have dealt with some of these issues if you use, for example, futures in Scala. Right? So it can be done, but it's much harder to think about the dynamic of the system. It's the same thing here. So when you're saying write, the big question for the client is, do you wait until the write got propagated everywhere and then you're sure that the write happened? Or do you go immediately and do something else, but then you must have a mechanism to notify you later that the write might have failed. There are many reasons that the write could actually have failed, right? And this is one of the choices that have to be made with this kind of a system, and it really depends on what consistency model you're trying to enforce, right? Now, a big issue always when you have things like home base is fault tolerance. The primary copy goes down, then what? So you have to augment this with mechanisms in which you decide who's the primary copy based on different protocols. And we talked already about the leader election protocols, right? I'm going to talk more about this, right? So that's one way to do things. Again, don't look for a silver bullet here. There's no such thing. There are solutions that have different properties, different compromises. So different kind of compromise would be done by this local write protocol. So in a local write protocol, you're going to write locally, right? But essentially what you're going to do to stay sane, I mean, everybody can write locally, and then you have to somehow resolve the conflicts, and that can have its own set of problems. But what you could do, and this is similar to those token-based protocols, is to get permission to own the local to have the right to write is the different rights, right, on your local machine. Right? So you say, temporarily, I'm the one that owns this resource, then I can do any rights I want to it, and later I'm going to give the ownership to somebody else. Okay? This could work and work nicely. So essentially you say, if you think about it, right, even though I use multiple clients, if I have this kind of local write protocol, this might work out reasonably well, right? So when I move to a new machine, I have to find out who's allowed to write and say, hey, I want to grab that privilege from you, which means you don't have it and I have it. I might have a little bit of a mildly tedious protocol to do so, but beyond that point, I can run very fast because I'm just going to write locally. Of course, the fault tolerance now suffers, right? Which, again, might or might not be a big issue for some of the activities you do. Okay? So, again, trade-offs versus trade-offs. Okay. Now, when it comes to rights, so I mean, there is vast literature on these issues, right? Because things can get very, very complicated, depending on the consistency model you're trying to enforce. So one of the things that you could try to do is the following. So if you have multiple servers, right, then one way to consistently propagate these rights, right, is to be careful who's allowed to write at what moment of time and who's allowed to read at what moment of time. Okay. So. One such solution is so-called quorum-based protocols. So the quorum-based protocols are protocols in which you have multiple participants, and they all have to participate in the act of either reading or writing, depending on how you actually do things. And of particular concern in this circumstance is to make sure that if somebody writes, nobody can read, or at least everybody's read copy is invalidated, right? So then one such possible solution, and this is a solution that's not good, and this is basically a solution that's good, right? So one way to make sure, for example, that you invalidate everybody else's copy is to basically say, let's say I need tokens to do any read or write in the system as a client, right? Now, to do a read, I might, and this is the situation with this circle here, right? If I get one token, I can read. But in order to write, I need all the tokens. Now, I mean, of course, the question is, you can come up with any protocol you want, but the question is, does it enforce the consistency model that you're looking for, right? Now, it turns out that this one will make sure that if anybody writes, nobody can read, and you cannot write if anybody reads. Is that the case? But notice that it's optimized for the reads. So if a single token is missing, you cannot write. You have to wait until you acquire all such tokens, right? Clearly, if you have all the tokens, nobody can read, right? So you can just reason through the scenarios, and you can see that both the reads and the writes are not going to be wrong. Now, of course, the problem is starvation for the writer, right? It might take a long time for the writer to acquire all the tokens in order to be able to produce that write operation. Okay? Yes? Right. So you can go. So you can go into such protocols and refine them. Now, one benefit of having separate. So you see, multiple readers are great, but then you need a mechanism to keep track of how many such readers exist or don't exist, right? So that's a choice in itself, whether you allow multiple reads or you don't allow multiple reads to happen. And also, what are exactly are these tokens and where are they and how do you keep track of them? One possible solution is to have a single dedicated, if you want, centralized server that just manages these tokens. It's very similar to the centralized solution that we had for the locking, right? And I mean, that's another way to do it. You can just use read locks and write locks in a centralized solution.
And if a client tries to make a write, it should acquire all, right?
Yes.
But if, for example, it tries to acquire A, B, C, they are not locked by other client, and they acquire them. But after this, it finds that D is acquired by another one.
Good.
It can't complete write, but it will release A, B, C, or
right. So many issues with this. And so this is what I'm trying to say with these protocols. You have to look at the tiny details. I mean, if such a protocol is published in a research paper, almost surely they show that it doesn't run into this kind of issue. So the issue is here deadlock, right? So the deadlock refers to the fact that if two writers start at the same time, they acquire some of the tokens, and then none of them can make progress because they are waiting for the other guy's token to be acquired, right? And that's it, you're stuck. So you must prevent such things to happen, right? I mean, what kind of mechanisms could you have to do this? I mean, one of them is to basically say if you don't acquire all your tokens within a certain amount of time, you release them. That might or might not work. I mean, all of these things could potentially be problematic depending on what is it that the token is. I mean, does it require a certain message exchange or doesn't require a certain message exchange?
Or we can do this like we are dealing with operating system such that releasing one node by one node and see what happens, or releasing almost that certain client have and see what happens.
Well, so what I want to point out, I mean, the details don't matter that much, okay? Because you literally have thousands of these protocols proposed. I mean, what am I going to do? Walk through all of them, right? What matters is to be aware of issues. So one big issue with anything that requires tokens or locks or things of this sort is deadlocks, right? So that's a tremendously big issue when it comes to any kind of synchronization. And by the way, so there are two things that eat you alive when you do parallel processing, right? One of them is race conditions. You forgot to lock and you access resources at the same time. And the other one is you locked enough to deadlock, right? Either of which are completely disastrous, right? And they have different ways of being disastrous, or they are completely disastrous. And by the way, even things that you might think should not ever run in trouble do occasionally run in trouble, right? In particular, for example, the operating system itself is, in fact, a mini distributed system. It needs to use synchronization. Because even if you don't have multi-threaded applications running multiple processes, is in fact some sort of a multi-threaded activity, right? It can actually happen, and this is, for example, what plagued operating systems for a long time. And this is where the blue screen of death comes into play and other such oops, for example, in the Linux kernel, in which, well, I mean, they're all humans, right? So they wrote code, and they were convinced it's OK. But at some point, somebody needed multiple locks to do an operation, acquired one of them, was waiting for the other one. Some other application had the lock and requires the second lock. And none of them could make progress because it waits for the other one to release the lock, right? And then what? Well, essentially, you have a deadlock. That means that resource is completely locked out, and nobody can ever access it until you reboot the operating system. The Linux kernel, for example, even have the PS program in Linux or most Unix operating systems has a special symbol for this, is D, which means it's deadlocked. By the way, if you see any process that has a D next to it, that essentially means maybe by a miracle, somehow something happens in the future and gets rid of it. But if not, next time, after you freshly reboot, the system is going to go away. There is no other way it's going to go away. And if it's about a very important resource, that could essentially mean you're forced to reboot the operating system, right? These deadlocks do still happen, even in things that are so pounded on for such a long time, like operating systems. When it comes to user programs, you can have lots of these things, right? Yes?
Performance. If we are trying to avoid or prevent deadlocks, then we are speaking about distributed systems. So this will
right. So I mean,
suffer with
Look. For everything, right? You can be very careful and very safe, but be slow or very fast and then run in some kind of trouble, or have solutions that, I mean, I don't want to go too much into these details because they are discussed in an undergrad operating system, right? I mean, I'm sure you took such a class, most of you, and you had all that deadlock prevention and deadlock detection, right? Deadlock detection is very costly. Deadlock prevention, it robs you of situations where you could have ran in parallel. So you have to give up something, right? And by the way, you might prevent deadlocks, but have something called live locks, in which you're still not making progress. You're just doing busy work, right? So for example, a live lock here would be, right? You try to acquire tokens for the write. But if you cannot acquire enough tokens within 1 second, you give up and start again. But you see, that still doesn't guarantee that anybody will go through and do anything. Why? Because if you have a bunch of these aggressive guys that want to do this, they wait the second and again go and steal some of the tokens. And again they give up and steal tokens. And again they give up and steal tokens.
Can be random. Not 1 second.
Yeah, but right. So you have to, maybe, but none of these things are really guaranteed to really work. Okay, random essentially means giving up performance, by the way. Right? So random restarts, which are used for wireless access most of the time when you have collisions on the channel, right? So one solution is to do this exponential backups, right? You start with 1 second, but if I don't succeed, I go to 2 seconds, 4 seconds, right? Ramp it up exponentially. You can actually, well, I mean, it's clear that somebody at some point succeeds because you keep on going exponentially back in the, I mean, you can even do some sorts of analysis depending on how many guys are trying to jump on it and how fast on expectation when you would do things. But keep in mind that if this is part of the things you do all the time, you might be robbed of tremendous amount of performance to do this, right? So if for every single item that you're accessing, you need to do this exponential backup, it's potentially a disaster. I mean, you're not doing anything except running this exponential backup algorithms, right? So when it comes to selecting such a, okay, let me back up even more. I want you mostly to be aware of this kind of things, the fact that it's tricky to get such a protocol running, right? That you have to ask hard questions about what is it that's going on and does it fit the specific application I have in mind, because some of them can work exceptionally well under certain circumstances and be disastrous under other circumstances. For example, under rare writes, this could actually work nicely. With very aggressive writes, this could actually be a disaster, right? But it's like this for everything else in this class, right? All of them have good points and not so good points depending on the circumstances. So when it comes to using distributed systems, the main question is which compromise fits my application, really? Right? Out of all the compromises that exist, as opposed to knowing what the good solution is. Right? In certain areas, it's known what the good solution is, and that's it, right? You can prove that that's the best solution, and that's the end of the story, right? But it's not the case here. For example, what's the best sorting algorithm? Even that's murky now, right? It used to be the case that the answer was easy, yeah, quick sort, but it's not so easy anymore. But then ask yourself, what's the penalty of not picking the right algorithm? Well, it's usually just a factor of 2, unless you do distributed sort, where it can be many orders of magnitude, but right? But things are not easy anymore because everything gets so complicatedly put together. Okay, right? So we still have. I'm sorry. Oh, 20 minutes. Okay, so when it comes to right, so when it comes to replication, right? We've seen. I mean, replication is the worst to a large extent when it comes to the decisions you actually have to make. Now you have to pair it up also with some sort of backups, right? In order to make the information really, if you want, permanent. And I mean, ultimately, for example, let's think about chat applications, right? I mean, for chat applications, again, you have to ask yourself the question is, what am I losing if everything goes away? Maybe, in fact, not so much. And I've actually, okay. Did anybody know anything about Snapchat? Okay. So this is, I didn't look at all the details, but I think this is mostly about, so they build in the opposite of fault tolerance into the protocol. It goes away after a while, right? Yes. Now this is one way to solve all your problems, right? So you can essentially solve all your problems with replication by not only not worrying about replication, but promising that you're not going to replicate, right? So apparently Snapchat, well, I mean, first of all, is valued at $3 billion, which, I mean, whatever. But apparently Snapchat is basically pictures or whatever, they go and the system will get rid of them in whatever short amount of time, right? So that basically means that you do exactly the opposite. I'm just trying to point out that certain applications go exactly in the opposite direction, right? So you're in fact promising not only that you're not going to replicate, but you're in fact promising that even on the client, you're going to destroy any such copy within a right? So it's exactly the opposite of caching. I'm going to cache for this amount of time and then destroy any copy I have, and it's gone. And whatever, it's cryptographically secure or whatnot. By the way, they should do cryptography, in fact. And that's, I know, and they kind of just rely on the fact that other developers are not smart enough to write another application that watches what the Snapchat does, right? But for example, cryptographically, well, by the way, this is a real problem. We have to discuss this. How do you make self-destructive messages, right? I mean, you see in some of the spy movies, right? This message will self-destruct in whatever amount of time. Now, if you literally have a small explosive device in a physical device, I mean, that's true, right? But, I mean, this is a real question. And, well, most of all, I think people like Snapchat are mostly irresponsible, right? They say, yeah, it's a cool application. We don't worry about anything in the world. They're not promising anything. They just kind of say, yeah, it's kind of OK, right? But imagine, for example, you're the US government, and you really want those things not to be available beyond a certain amount of time. How would you do it? Right? These are very hard questions to in fact, answer. And to some extent, you need to put together multiple pieces of some sort of a key and make that unavailable somehow. I mean, the big problem is what? If I could read it once, what would prevent me from reading it again, unless I have some physical mechanism that prevents that from happening? Right? So that's, but there are interesting questions with respect to that. For example, also with when it comes to, for example, secure access to a resource. Right? How many of you, and this is a kind of an interesting maybe preview to security, but how many of you have seen those tags people wear on the keyring or on the neck that have some sort of a weird counter that keeps on counting, and they use that to log in into a website. And that counter is valid for about 30 seconds or whatever. So what's that stuff?
It's a one-time password, right? So it's kind of with your identification, you put that number in and they can identify whether you.
Right, but the key for all of those things, right, is the fact that they're unforgeable, right? Well, I mean, look, by the way it works is very simple. It literally has a counter, 1, 2, 3, 4, and you push it through AES-256 or through some kind of a public key cryptography mechanism, and you simply take what comes at the other end, right? Now, remember what I told you about public key cryptography. It's so good that even if you know what you put in, you cannot predict what comes out, right? And in fact, will produce a sequence that cannot be forged without knowing the key. Right? It doesn't matter how many pairs of input outputs you have, unless you get very, very close to 2 to 200 or something like that. You're not going to be able to guess what the key is, and you need a key in order to predict the next number in the sequence. So those are, to a large extent, unpredictable numbers unless you somehow extract the key from the physical device. Right? OK, more discussions about that. So when I discuss about security, somebody has to remind me to talk about physical attacks on secure systems, because I have a number of cool stories to tell. Okay, physical attacks. All right. So let's start talking a little bit about fault tolerance. So we've seen the, concurrency replication. One major reason to do replication was fault tolerance. Another one is increased performance, right? All right. So when it comes to fault tolerance, let me just warm up the discussion about fault tolerance with the issue of how do you know something is faulty? Right? So let's even forget about all the formalism and all the stuff that needs to be discussed when it comes to fault tolerance. It's basically, OK, you can say, if something is faulty, I'll do something about it. Replicate, switch another replica, switch to another server. How do you know something is faulty? Right? So let me put some stuff on the board. The question is, what is faulty? how do you know something is broken? I mean, faulty means broken in some way. Right? So all of these things need to be somehow monitored. I mean, when it comes to faulty, you can think about self-diagnosis. Maybe it works, maybe it doesn't. Right? So maybe self-diagnosis would work for this. I monitor myself and I realize I'm broken. I mean, some of the cars monitor themselves and start screaming if they don't like something. Sometimes it's nothing and they just annoy you, right? It's a red light comes on and hey, something is faulty. So maybe self-monitoring. Maybe. The other one can be peer monitoring, right? For example, peer or client monitoring. Right. You could also have physical devices that monitor. For example, this is kind of interesting, and you can actually buy all of this stuff. They sell devices now that can, in fact, monitor whether a computer system has power or doesn't have power or is in some sort of a bad state. And then those devices can be used to remotely reboot a machine. Right? So it's important that the monitoring, as much as possible, it's an independent physical device from the primary device because the fault could be related to a global system failure. Right? If you have partial system failures, you can imagine that you have some sort of self-monitoring going on. But if it's a global system failure, you must have another system to monitor this system. Right? Now, let's think about the kind of faults that can happen. Right? So what kind of faults could I have? Well, I mean, all of the servers or all of these computers run some program. So the program itself can have bugs. I mean, so causes of faults. Let's think about that. Right? So I think the primary cause for bugs is, in effect, software defects, bugs. 1S. Right? OK, so we can have bugs. Software bugs. So let's say software bugs. We can have hardware bugs, less nowadays. By the way, do you know why bugs are called bugs?
Yes. When the first programs were wires, programming were with wires, wiring switch 0 and 1, and when a program was not working,
right.
a programmer that was trying to know the problem found a bug inside.
Right. So for the people that probably couldn't hear you, it's basically literally found a physical bug in one of the circuit boards in one of the early computers, and they call the whole process debugging, finding the bug. Okay. All right. So we can have software bugs, we can have hardware bugs. Now, I want you to understand that these computer systems are not super fragile, but are somehow influenced by various external things, and a lot of these bugs could be caused by external things. I mean, for example, when it comes to faults, one fault is basically the power goes down. I mean, that's one of the bigger faults, right? Power failure. This definitely could do it. Right? But let me give you an idea why it's impossible to have a system that doesn't have at least eventually some kind of hardware bugs. Okay? So one of the things that almost surely will start producing havoc is the temperature rising for whatever reason. So it turns out that, well, because of thermodynamics, right, the higher temperature means bigger agitation on the atoms, which essentially means that clean 0 and 1 state that can be kept separate from each other unless you want to do a state transition can actually automatically transition from a 0 to 1. And by the way, this is actually, I might as well tell you this, because this looks like a bug, but can be used as an interesting feature when it comes to security attacks. So there is a group. I'm going to tell you the whole story when I talk about security, but there is a group at, I think, Harvard that's known for completely crazy security attacks. And one of their attacks is based on increasing the temperature. Okay? So essentially, they showed how you can exploit a machine, or the Java virtual machine, by increasing the temperature. Because when you increase the temperature, you produce these random flips between 0 and 1. And they showed a particular layout in memory for a Java program that will allow a single bit flip to be exploited and to do anything you want with the Java virtual machine, right? So essentially, all you have to do is heat up the temperature in the room, right? The memory is the first one to go when it comes to heating up, because you're going to start having those 0 to 1 transitions in the memory. But there are other things, by the way, that transition automatically, and this is why servers have error-correcting memory, right? For example, cosmic rays, which do happen, right? One goes through, it will actually produce a flip. And they don't happen too often, but I mean, a server like this can stay up for a year, right? It's bound to have at least one of those going through the memory and flipping something. By the way, this is where the actor model in Scala comes into play, and actually the actor model in Erlang, which was introduced for this. Rather than design systems that never fail, you embrace failures and you embrace monitoring, either self or peer monitoring. And you can have actors monitoring other actors, and essentially you say, this guy, it's in a weird state, let's kill it and start it again to recover some sort of a good functioning of the system, right? So one way to deal with fault tolerance is to design systems that are more fault tolerant. And that's, for example, the approach taken by Ericsson with Erlang. They designed self-healing systems or things of this sort. And that definitely will alleviate the fault tolerance problem. Or you could say, let it fail and then I'll do something else. But then you still have this issue with how do you detect failure, right? So software bugs, hardware bugs, power failure, but there is a special kind of failure that it's extremely hard to protect against, right? It's something I mentioned before. It's called Byzantine failures, right? Or let's call them malicious failures. Nobody remembers why they are called Byzantine failures. There is no direct connection with the Byzantine Empire or whatnot. So let's call them malicious failures. So the malicious failures are of the following kind, okay? And this is why it's really, really, really hard to protect against them. Instead of having one of these natural causes for the failure, and then the monitoring will do it, somebody goes in, takes control of the machine, and make it do slightly different things. If they really know what they're getting into, they could wreak havoc on the entire distributed system and not only that machine alone, right? For example, imagine any of the distributed protocols running in which one of the participants is not playing by the book. And it's not playing by the book because every now and then it hiccups, which could happen. It's not playing by the books intentionally to wreak havoc on the distributed protocol, right? So for example, I mentioned here with the writes, right? The fact that they are going to do exponential backup. What if one of the guys never does exponential backup and just takes one of the tokens and never gives it away? That essentially means nobody writes. By the way, that's a form of distributed denial of service attack, right? So this kind, especially malicious failures, are a tremendous problem right now in general, right? We're going to discuss some of these failure protection mechanisms that can deal with malicious failures, but in fact, you have to pay a dear price for it, right? The same resource has to be available in multiple places, and somehow you're monitoring to see if somebody is lying, and beyond a certain point, there is nothing you can detect. So a crucial question is, for example, let's think about peer-to-peer systems, right? So let me give you an idea just how far this can go. So not only that some participants can be malicious, the whole system can be malicious, right? So one of the things that surfaced is that one peer-to-peer system that started to be quite popular, I don't remember the name, in fact was only a honeypot for the music industry to catch people that are interested in sharing music, to make a list of who to sue, right? So to some extent, the whole system was faulty in a certain sense, and not only some participants. But another way you can think about it is, hey, could I participate, or could I prevent this? Could I participate in a peer-to-peer system and by being maliciously faulty, disrupt the peer-to-peer protocol, right? You just finished one of your projects, right? Imagine that some of those guys would not play by the book. Can you imagine ways in which they could disrupt completely the system, right? They can partially disrupt the system by taking any message that's routed to them and throw it as wrongly as possible, right? That will slow things down a little bit. You can even compute how much you can slow it down. So a crucial question, for example, for that is, how many peer-to-peer participants would you need to disrupt most of the function of a peer-to-peer system if you use a distributed hash-table peer-to-peer system? I'm sure there is some serious math that can be done there to do some probabilistic computation to say, 10%, it's enough, nobody will get any work done, right? For example, if you really throw the request all the way around in the wrong direction, right? If the probability that one of your guys is hit is reasonably high, then essentially you can make sure that none of these protocols finish. or finish in a reasonable amount of time. Basically, take the performance down by an order or two orders of magnitude. Okay? So these kind of failures are going to be very hard to deal with because it's hard to tell when such a failure kicks in. So a big question is, okay, fine, you do monitoring, but how would you know that somebody is malicious? So to some extent, you need to collect information in what you believe are non-malicious nodes, or in a lot of nodes, some of them malicious, some of them non-malicious, and somehow to compute some sort of are you malicious or non-malicious property to tell if somebody is malicious. Once you detected such a failure, you can isolate that node through whatever mechanisms. For example, you could use multicast or some sort of broadcast to say, don't trust that guy and kick it out of the network. But again, the problem is, how do you know it's malicious? Okay? And it's a cat and mouse kind of situation, which is true for almost anything related to, in fact, security. Okay? Right. So again, what is faulty? How do I know? So I'm a different system. How do I know somebody else is faulty? Let's not worry about malicious because this is just hard. We need a discussion separately. But there are participants, and we talked about this, right? The Bully algorithm and some other lethal election algorithms, right? Those algorithms needed some sort of a leader, and without the leader, the system doesn't work. So you have to somehow determine when the leader is faulty to elect another leader. For example, that's one of the basic things you could do, right? So what does monitor mean? Right? Mechanisms need to be built in order to be able to declare somebody faulty. So when you declare somebody faulty, you have other issues to deal with. One of them is the fact that, okay, I declare somebody to be faulty. I let other nodes know that it's faulty, but maybe the guy did turn out not to be faulty in the end, and he comes alive. For example, in leader election, that could create problems because if you have two leaders at the same time, then what? The guy that wasn't faulty or is not faulty anymore comes back. You already have another leader, and would your protocol run with two leaders? Would this old guy figure out that there is a new leader? How? Always need kind of message exchanges. So the classic example of how you could detect at least normal kind of faults is keep alive, right? Keep alive messages. Or heartbeat. It's actually heartbeat, sorry. The keep alive is how this heartbeats go, so heartbeat. Okay, so heartbeat mechanism consists in having special kinds of messages that are sent at regular intervals of time. And the lack of those messages lead to somebody being declared dead. It's like taking the pulse of somebody. If they don't have 10 successive heartbeats in a certain amount of time, you say they are dead. Okay? So this is exactly what this is. But that essentially means that you're trading performance for fault tolerance, for fault detection. In particular, you must send its heartbeats, because if you miss the heartbeats, then you will be declared faulty and potentially kicked out of the network. Yes?
What are the chances that the machine is doing something and cannot process the heartbeat? Might be live, but...
Good. So this is a very good question. So when it comes to heartbeats, there are two questions to ask. One is how often do you send them, and the other one is after how many missed heartbeats do you declare somebody dead? Right? And these things is not enough to do this, right? I mean, ideally, you would treat these heartbeats as extremely high priority messages, right? In the sense that even if the machine is super busy, right, you would like to still send a heartbeat to say, I'm alive, don't kill me, no matter how busy I am, right? Which is not necessarily a simple or easy thing. So the fact that you can do something like heartbeats, it doesn't mean it will just work without problems all the time. Right? And in particular, a big worrisome thing is you declare lots of things as being dead when they're not dead at all. It's just some kind of a temporary hiccup. Right? So, for example, if you have stormy weather outside, you easily can have no internet connectivity for, let's say, half a second. Right? Because in that amount of time, there is too much electrical charge and nothing goes through. If you require a heartbeat every 30 milliseconds and on 3 heartbeats you're declared dead, then you declare dead half the network. Right? So it's not going to be good. So it's tricky exactly how you use it, how you fine-tune it, and what you do with it, but at least it's some sort of a mechanism that could be used to detect something. Look, the easy way out is to say everything is too complicated and I'm not going to do anything, but that's not quite an option when it comes to engineering, right? So that's what I want you to keep in mind. All of these things are compromises. All of them have black spots here and there, right, dark corners. Sometimes they are not doing exactly what they are supposed to do, but you still need some mechanism to deal with the situation. So I'm going to obviously discuss more about this on Thursday, and we're going to continue discussing the fault tolerance with all of this replication in mind, because that's one reason to do the fault tolerance. It's not enough to detect failures. You have to do something about it, and that almost always means some solution around replication. Okay. All right.